let's take a look at this theorem 4.16, and I'm wanting to prove it because it is sort of what is the point of this. The point is that the set of solutions is a subspace, particularly to the homogeneous system. If it's not the homogeneous system, it's not a subspace. All right, so let's go ahead and get a proof going here. So again, let's let A be an m by n matrix. And n of A, the set as written above, x in R, to the n, such that Ax equals the 0 vector. So if we multiply A by x, we get the 0 vector. All right, so we want to show, let's remind the readers of this, to show that n of A is a subspace of R to the n using this subspace test. So now we have to go back to 4.3 and remember how that works. All right. So that works as follows. So first off, we want to show that this is non-empty. So think for a moment, is there one thing that you can guarantee for certain is a solution to A times x equals 0? All right, so let's notice that A times the 0 vector is the 0 vector. So the 0 vector is in n of A, and n of A is non-empty. Right, excellent. Second, let's test additive closure. All right, so when we're testing additive closure, we want to start with two generic things. So U and V be in the null space, n of A. All right, by definition, this means that A times U is the 0 vector and A times V is the 0 vector. All right. So again, let's write down that we want to show that U plus V is in the n of A. All right. So again, let's think about what that means. So that should mean that A times the 0 vector, or A times U plus V equals the 0 vector. So let's test this. Is A times U plus V, right? Well, we can use distributivity. Distributivity of matrix multiplication. Okay, but now we know what A times the U is, and we know what A times V is. So this is our assumption that allows us to make this change. And 0 vector plus 0 vector is the 0 vector. Let's just throw that in. All right, so therefore, A times U plus V equals the 0 vector, so U plus V is in n of A. All right. And I notice when you're doing proofs, a lot of you are omitting a lot of these like conclusion sentences. But if I just stopped at that line with 0, I'm covering it up with my hand, but you can't see. If I stopped right here, then there's sort of a question of like, oh, well, does that mean what we want it to? I don't remember. Let me go back. Assume your reader is lazy and doesn't want to go back and do anything. So you should tell them, hey, this is what we wanted to show, and we showed it. Okay. All right. So 3. Lastly, we need to show scalar closure. So let's let C be a scalar. We want to show now we're going to use the U from above. That C times U is in the null space. Okay, so how do we do that? Again, let's test that A times CU, right, is CAU, okay, and that is scalar factoring, which was one of our axioms of matrix multiplication if you want to look back at chapter 2. All right, and that's C times the zero vector by assumption. And when we scale the zero vector, we get the zero vector. So actually that we could even say that that's theorem 4.4. Right. So therefore, again, we want to conclude C times U, or A times CU equals the zero vector. So CU is in the null space. Okay. Again, we don't want to just stop there. We want to remind the reader that we've actually proved something important and exactly what that important thing we proved was. So we conclude by the subspace test that n of A is indeed a subspace of R to the n. Alright, there we are, QED. Fill in our box, say we're done, let the reader know. Alright, so that's the proof. I hope it was enlightening. I hope it was good to get a refresh of how subspace test worked, and I hope you have a good one. Bye-bye.